All right, diving right in today. We're taking a deep, deep look into water splitting.
It's a process that holds, well, huge potential, for a future where energy is truly sustainable.
And we're talking specifically about the production of green hydrogen.
That's right.
Now, if you're someone out there who's deep in the world of chemistry or material science, like maybe you're a BSc student, you're working on your master's, maybe even a PhD, this is for you. This exploration, this whole deep dive we're about to take, it's designed to give you a really solid grasp of the fundamentals here.
And we want to keep it engaging, right? We want to highlight the most important takeaways about how nanocatalysis is really like revolutionizing this field.
Exactly. We're all about extracting those key insights, those aha moments. We don't want to drown you in details. We want to get to the core of it.
Yeah, we really want to focus on that core.
All right, so to kick things off, let's set the stage. The idea of splitting water into its biggest components, hydrogen and oxygen, this isn't exactly a brand new concept, is it?
It's actually quite fascinating. The idea of using electricity to split water, that's electrolysis, and that concept was, well, it was understood way back in the 1800s, 1839 to be precise. A guy named Sir William Grove demonstrated it.
Wow, so almost 200 years ago. Yet it feels like it's only just now, with this, very urgent need for renewable energy sources, that water splitting is getting the attention it deserves.
And that's a great point. It really highlights how the most crucial thing isn't always just the fundamental discovery. It's often how you apply it, how you scale it up to actually meet real-world demands.
And the applications for hydrogen are pretty diverse, right? I mean, it's not just about using it as a fuel source. It's used in a bunch of different industries.
Yeah, absolutely. One of the big areas is fuel cells and energy storage. Hydrogen can be used to store energy generated from renewable sources like solar and wind. So when the sun isn't shining or the wind isn't blowing, you can convert that stored hydrogen back into electricity. Super important for a stable energy grid.
Makes sense. So it's like a clean energy buffer.
Exactly. Then you have its use as a feedstock in industry. We're talking ammonia production, which is essential for fertilizers and food production.
Oh, wow. So it even plays a role in agriculture.
Absolutely. It's also crucial in steel manufacturing and lots of different chemical processes that are like essential for our modern world.
Right. It's woven into so many aspects of our lives. And the whole push towards decarbonization, that's really where green hydrogen shines, isn't it? It offers a way to create QO-free energy solutions for transportation, manufacturing, heavy industries, those sectors that have traditionally relied on fossil fuels.
And it's those sectors where the potential impact on reducing greenhouse gas emissions is absolutely massive. We're talking about a real game changer in the fight against climate change.
Okay, so big potential, for sure. But I know there are challenges with scaling up water splitting. What are some of the hurdles that researchers are trying to overcome?
Yeah, there are definitely challenges. One of the big ones is the energy requirement. It can take a significant amount of energy to split water efficiently. Also, the catalysts that help facilitate the reactions can sometimes degrade over time, which reduces their effectiveness. And of course, there's the cost factor. Making green hydrogen production cost competitive with traditional methods, those that use fossil fuels, that's a huge focus of research and development.
So that's where nanocatalysis comes in.
Exactly. Advancements in nanocatalysis are aimed at overcoming these very challenges, making the process more efficient, more durable, and ultimately more affordable. That's what's going to make green hydrogen a true reality.
All right, let's get down to the chemistry here. We all know that water is H2Os. But splitting those hydrogen and oxygen atoms apart, that's not just reversing how water is formed, is it?
Nope, not at all. We're talking about two distinct electrochemical half reactions happening at the same time. But they happen at different spots within the water splitting system. We've got the hydrogen evolution reaction, HR for short, and that takes place at the cathode. It's the negatively charged electrode.
Okay.
So the equation for that is 2 height plus 2A yields H.
So that's how we get hydrogen gas.
Right. But to make this happen efficiently, we need catalysts. Specifically, hydrogen evolution catalysts, or HECs. They lower the energy barrier for the reaction so it happens more readily.
And on the flip side, at the anode, the positively charged electrode, we have the oxygen evolution reaction, OER. And if I remember correctly from my own chemistry classes, that one is a bit trickier.
You remember correctly. The OER is more complex. It's kinetically, sluggish compared to the HR. Yeah, it just doesn't want to happen as easily. And part of that is because it involves the transfer of 4 electrons compared to just 2 in the HR. More electrons means more steps, more complexity, a higher energy barrier. Imagine like juggling 4 balls at once. It's a lot harder than 2.
We can see that.
So we need really robust oxygen evolution catalysts, OECs. These are essential to drive this reaction at a practical rate. It's often the bottleneck in the whole water splitting process.
Okay. 2 reactions, HR and OER, both essential. Now, how do we actually provide the energy needed to kickstart these reactions? I know we've mentioned electricity and light.
There are 2 primary approaches, electrocatalysis and photocatalysis. With electrocatalysis, you apply an electrical current. Ideally, this comes from a renewable source, like solar or wind power. That current provides the energy to overcome those activation barriers for both the HR and the OER, all within an electrochemical cell called an electrolyzer.
So it's kind of like using electricity to force the water molecules apart.
That's a good way to think about it. And then there's photocatalysis. This approach uses light energy, most commonly sunlight. When light hits certain semiconductor materials, it energizes electrons within the material. These excited electrons can then drive those water-splitting reactions directly at the material's surface.
Okay, so with photocatalysis, it's like the material itself is absorbing the energy from sunlight and using it to break apart the water molecules.
Exactly, like a tiny self-powered water-splitting machine.
That's pretty cool.
Yeah.
So let's dig deeper into electrocatalysis first. It seems like that might be more readily applicable with our existing electrical infrastructure.
Yeah, you could say that. So in an electrocatalytic water splitter, you have these 2 electrodes, the anode and cathode. They're submerged in a special solution called an electrolyte. This electrolyte helps the ions move around. When you apply a voltage across the electrodes, you create an electrical field. This field drives the movement of ions, and that provides the energy to get those catalytic reactions going at the surface of the electrodes. You get hydrogen gas bubbling up at the cathode and oxygen gas at the anode.
So it's like a controlled chemical dance, all orchestrated by electricity.
That's a good analogy.
Now, what are the key things we need to consider when designing an efficient electrocatalytic system? I imagine it's not just about choosing any material that conducts electricity.
You're absolutely right. It's much more nuanced than that. There are a few key performance indicators that really matter. Energy efficiency is at the top of the list. That basically means minimizing the overpotential.
Overpotential. Remind me what that is again.
It's the extra voltage you need to apply on top of the theoretical minimum voltage to actually drive the reaction at a useful rate. It's like needing an extra push to get a heavy object moving. The less extra push you need, the more efficient the process is.
Makes sense. So lower overpotential means less energy wasted.
Exactly. Then there's catalyst stability. Remember, those catalysts are doing all the heavy lifting, making the reactions happen. They need to be able to withstand the environment inside the electrolyzer, which can be quite harsh. They need to hold up over long periods of operation without falling apart or losing their effectiveness.
Durability is key.
Absolutely. And of course, the choice of electrode material is super important. It needs to be a good conductor of electricity to minimize energy loss, and it needs to provide a stable platform for those nanocatalysts to do their thing.
Okay. Now, I always hear about platinum being the gold standard catalyst for the HR. Why is that? What makes platinum so special?
Platinum is, well, it's really good at its job. For the HR in acidic conditions, platinum is incredibly efficient. It has this almost perfect ability to grab onto hydrogen ions and help them combine to form hydrogen gas. This results in a very low overpotential, which means high energy efficiency.
So platinum is like the star athlete of hydrogen evolution catalysts.
Haha, in a way, yes.
But there's a catch, right?
There is. Platinum is a precious metal. It's expensive and not exactly abundant. And those are big barriers to using it on a large scale, like we'd need for widespread green hydrogen production.
Makes sense. So a lot of the research then is focused on finding less expensive and more abundant alternatives to platinum.
Precisely. There's a lot of excitement around earth-abundant transition metal catalysts. Molybdenum disulfide, nickel-based alloys, cobalt-based compounds. These are materials that are much more common and therefore much cheaper. And through clever nanomaterial design, researchers are getting these materials to perform incredibly well. Some of them are even rivaling platinum in terms of activity, especially when you factor in cost.
That's really encouraging. Now, what about these single-atom catalysts I keep hearing about? What are those and why are they so exciting?
Single-atom catalysts are a really cutting-edge idea. It's all about maximizing efficiency. You see, with traditional nanoparticle catalysts, you have a bunch of atoms clumped together. Many of these atoms are buried inside the nanoparticle and don't actually get to participate in the reaction. They're just along for the ride.
So it's like having a whole team, but only half of them are actually playing.
Exactly. But with single atom catalysts, you have individual metal atoms dispersed on a support material, like tiny individual workers spread out on a factory floor.
Okay, I get it.
This way, almost every single atom is exposed and able to take part in the reaction. That means you use less material, which can be especially beneficial when using expensive metals. And because these single atoms have unique electronic properties, they can be exceptionally active and selective catalysts.
It's all about working smarter, not harder.
Exactly.
Now let's talk about the OER. What are the go-to catalysts for that side of the equation?
Well, similar to the HR, the most active OER catalysts, particularly in acidic environments, are precious metal oxides, specifically iridium oxide and ruthenium oxide.
Okay, so back to those expensive metals.
Yeah, unfortunately. But, like platinum for her, their scarcity and high cost are big obstacles for large-scale deployment.
So again, the need for more sustainable and affordable alternatives is paramount.
Absolutely. And there are some promising contenders. Nickel iron oxides have emerged as a very attractive alternative, especially for alkaline electrolyzers, which, as we discussed, operate in more basic conditions. These nickel iron oxides are made from cheap and readily available materials, and they perform well in alkaline environments, showing good activity and stability.
So they're practical for real-world applications.
Exactly. They're a viable option for current and near-future green hydrogen production.
And you mentioned perovskite oxides earlier. What makes them interesting for OER catalysis?
Perovskite oxides are a class of mixed metal oxides with a very particular crystal structure. And what's really cool about them is that you can tune their electronic and chemical properties by carefully selecting the metals you use and how you put them together.
So it's like having a toolbox of different metals, and you can mix and match them to create a catalyst with the exact properties you need.
Exactly. You can essentially design the catalyst from the ground up. And that's what makes perovskite oxides so exciting. They offer a huge amount of flexibility in tailoring catalysts to specific applications.
That's really fascinating. Now, I know there are different types of electrolyzers out there. Does the type of electrolyzer influence the choice of catalyst?
Oh, absolutely. The electrolyzer design and operating conditions play a big role in determining the best catalyst. Alkaline electrolyzers, for example, they operate in a basic high pH environment, so they can use those more cost-effective nickel-based catalysts and nickel iron oxides. They're stable under those conditions.
Okay.
But proton exchange membrane electrolyzers, PEM electrolyzers, they operate in acidic environments, much harsher conditions. They need catalysts that can handle that acidity without falling apart.
So those precious metal catalysts are often preferred for PEM electrolyzers.
Yeah, but research is really pushing to find earth-abundant alternatives that can also hold up in those acidic conditions. And then you have solid oxide electrolyzers, SOEs. They operate at really high temperatures, like hundreds of degrees Celsius, so the catalysts for those need to be able to withstand those extreme temperatures.
It's like each electrolyzer has its own personality and needs a specific type of catalyst to match.
That's a great way to put it.
Okay, let's switch gears now and talk about photocatalysis, using light to split water. How does this approach differ from electrocatalysis?
With photocatalysis, instead of an external electrical voltage, you use a special material called a semiconductor photocatalyst.
Okay.
When this material absorbs light, sunlight in particular, it gets excited. Electrons within the material jump to a higher energy level, and this creates what we call electron-hole pairs.
Electron-hole pairs.
It's like creating a separation of charge within the material.
Yeah.
You have these negatively charged electrons that are energized and ready to go, and you have these positively charged holes that are left behind. And these energized electrons and holes, they can migrate to the surface of the material and drive the reactions. The electrons can reduce water to hydrogen, and the holes can oxidize water to oxygen.
So the material is absorbing light energy and using that energy to directly split water.
Exactly. It's like a miniature solar-powered water-splitting factory.
Pretty amazing. Now, what makes a good photocatalyst? Are all semiconductor materials equally good at splitting water?
Not at all. There are a few key things that make a semiconductor effective for photocatalytic water splitting. One of the most important is its band gap.
Band gap. Refresh my memory on that one.
It's the energy difference between the valence band, where electrons normally hang out, and the conduction band, where electrons can move freely and conduct electricity. So when a photon of light hits the material, it needs to have enough energy to bump an electron across that band gap. And for that to happen efficiently with visible light, which is the most abundant part of sunlight, the band gap needs to be in a specific range. around 2 to 3 electron volts.
So if the band gap is too big, the material won't absorb enough sunlight.
Exactly. It'll only absorb the higher energy UV light, which is a much smaller portion of the solar spectrum. Another important factor is charge carrier separation.
So you want those electron hole pairs you created to actually do something useful.
Precisely. We want to prevent them from just recombining and wasting all that energy. If they recombine too quickly, they won't have time to reach the surface and participate in the water splitting reactions.
Okay, that makes sense.
And the last important factor is the density of active sites on the surface of the material. Those are the spots where the actual water splitting reactions happen. More active sites mean a more efficient catalyst.
It's all about providing those electrons and holes with a place to do their work.
Exactly.
Now, what are some of the key nanomaterials being investigated for photocatalytic water splitting? Are there any frontrunners?
Titanium dioxide, TOU, was one of the early favorites. It's pretty stable and inexpensive, but as we mentioned, its band gap is a bit too wide. It mostly absorbs UV light, not visible light, so a lot of research is focused on materials that are better at capturing visible light.
Okay, so what are some of those materials?
Graphitic carbon nitride, or GCO, is a really promising one. It's metal-free and can absorb visible light. Bismuth vanadate, BO, is another one that's shown a lot of potential, particularly for the oxygen evolution reaction. And researchers are also looking into various other metal oxides, sulfides, and even some more exotic materials.
So lots of options on the table.
Yeah, the field is really exploding with possibilities.
Now, are co-catalysts used in photocatalysis, just like they are in electrocatalysis?
Oh, absolutely. Co-catalysts are essential in photocatalysis too. They're often nanoparticles that are deposited onto the surface of the main semiconductor photocatalyst, and they help to facilitate either the HER or the OER. For example, platinum nanoparticles are often used as a co-catalyst for the HER. They can really lower that overpotential and make hydrogen production more efficient.
So platinum is still a valuable player, even in photocatalysis.
It is, but again, there's a big push to find Earth-abundant alternatives. Cobalt phosphide, COP, for example, is showing promise as a cheaper HER co-catalyst. And for the OER, nickel hydroxides and oxides are often used. They help those positively charged holes react with water molecules more efficiently.
So it's a team effort, even at the nanoscale.
Exactly.
Now, how are these photocatalytic materials actually used in a water splitting system?
There are two main approaches. One is called a suspended particle system. That's where you have nanoparticles of the photocatalyst just floating around in water. You shine sunlight on the water, and the particles absorb the light and start splitting the water molecules. You then collect the hydrogen and oxygen gases that are produced.
So it's like a tiny underwater solar farm.
That's one way to think about it. The other approach involves using photoelectrochemical cells, or PEC cells. In these systems, the semiconductor photocatalyst is used as an electrode. It's immersed in an electrolyte solution, and when sunlight hits it, it generates those electron hole pairs. And sometimes you apply a small voltage to help separate those charges and boost the efficiency.
So PEC cells are kind of a hybrid between photocatalysis and electrocatalysis.
Exactly. They bridge the gap between the two approaches.
Okay, so we've got these two promising pathways to green hydrogen,
Yeah.
electrocatalysis and photocatalysis. Where do we stand right now in terms of actually using these technologies in the real world?
Well, electrocatalysis, specifically PEM electrolyzers, are already commercially available. So in terms of industrial implementation, electrocatalysis is a bit further along.
So it's already happening.
It is, but a lot of the focus right now is on bringing the cost down, especially the cost of those precious metal catalysts. Making the technology more affordable is key for widespread adoption.
Makes sense. What about photocatalysis?
Photocatalysis is super promising, especially for creating low-cost, decentralized hydrogen production. Imagine small-scale systems producing hydrogen right where it's needed, powered by the sun. But the technology is still mostly in the research and development phase. We're seeing really good progress in the lab, with efficiencies steadily increasing, but there are still challenges with scaling up these systems and making sure they're durable enough for real-world conditions.
So more work to be done, but lots of potential.
Definitely.
As we look to the future, what are the biggest challenges that need to be addressed to truly unlock the potential of water splitting for a sustainable energy future?
One of the biggest, as we've talked about, is catalyst cost and scalability. We need to develop catalysts that use earth-abundant materials, catalysts that are cheap to make and can be produced on a large scale. That means moving away from those precious metals.
Right, finding those affordable workhorse catalysts.
Exactly. We also need to keep pushing the efficiency of the entire process, both in electrocatalysis and photocatalysis. Every little bit of improvement can make a big difference. And beyond the actual water splitting, we need to figure out the best ways to store and transport hydrogen safely and efficiently.
So the infrastructure surrounding hydrogen needs to catch up.
Yeah. And finally, it's essential to integrate water splitting technologies directly with renewable energy sources. We want to make sure the hydrogen we produce is truly green, generated using solar, wind, or other clean energy sources.
So it's not just about the hydrogen itself, it's about the entire energy ecosystem.
Exactly. It's about creating a truly sustainable energy loop.
Well, this has been a truly incredible journey. We've gone from the basic chemistry of water splitting all the way to the cutting edge of nanocatalysis research. It's amazing how much complexity is packed into this seemingly simple idea.
It really is. And for all those listening who are studying or working in chemistry or materials science, I hope this highlights how important your fields are in tackling this global challenge.
Designing those next-generation catalysts is going to be key to unlocking a green hydrogen future.
Absolutely. And for those researchers out there, there's still so much to explore. How can we design even better catalysts? More active, more stable, more affordable? How can we translate those exciting lab discoveries into real-world technologies?
These are the questions that are going to shape the future of energy.
And the answers are out there waiting to be discovered.
For everyone listening, think about this. If we can truly master efficient and affordable water splitting, powered by renewable energy, what would that mean for our world? How would it change our relationship with energy, our dependence on fossil fuels?
It's a powerful question to ponder.
It is, and one that's worth exploring further. Thanks for joining us on this deep dive.
It's been a pleasure.